and then he got fed. I think we kind of successively got fed up doing it. So after each rewrite, I'd work on it for a couple of weeks, get fed up. That's it. Over to you. And then you rewrote it.
And the whole time we're developing our ideas and also our understanding of what the actual problem was, or what the problem was.
Yeah. Right. And what you see today.
What was that problem?
That was to build fault-tolerant systems.
Okay, and by fault-tolerant?
We mean systems that go forever. I mean, we took the view that both hardware and software failures are going to occur, and that we won't be able to do anything about that. They are going to occur. So after the event, we have to correct them.
Right.
And we were building what we knew were going to be massively distributed systems. So in a sense, that Erlang is kind of interesting today. It's because we were solving those same problems back in the mid-80s.
Right.
And then right in the middle of the 90s, then the guys who are building big clouds and things like that, the rack-faced people, then realised that actually that's the same as the problem we were looking at in the mid-80s. So that's why we've got a bit of a head start on a lot of other technologies.
Okay. And also one of the basic concepts between the fault tolerance is accepting, well, as Joe said, accepting the fact that there are going to be errors. Things are going to crash in the system, but the system as a whole must not crash.
Yeah.
Right.
That's the fundamental principle behind the error handling.
Okay.
The system must not crash.
Right.
And things will crash in it.
Yeah. And there was also a kind of philosophical difference in how you handle errors, because everybody else is doing it wrongly, because they try and handle errors locally.
Okay.
And we said you can't handle errors locally, because if the whole machine crashes, how do you handle the error? So the smallest unit of fault tolerance is 2 distributed computers. So this guy, that performs computations, that guy is responsible for error recovery, and they must be on different machines. They cannot be on the same machine, because if this whole machine crashes, you're lost.
Right.
And that turns out to be, I didn't realise it at the time, the same thing you need for scalability. Because once you've done the architecture to split it into 2 things, it's not only fault tolerant, it's also scalable.
Right.
Well, yeah, because once you've made it work on 2, the step on making it work in a 3 is quite small.
Yes,
and once you've done 3, you can do 4 and
10,
5.
or a million.
You've got the basic principle.
Or a trillion.
Or a trillion. Well, we haven't got to a trillion yet.
And that's why it's going to run forever, you see, because once you've put your software onto a trillion machines, they're not all going to stop.
At once.
Hopefully. Hopefully. Not even if the cleaner pulls the plug out too much. Use the vacuum.
And the other thing, which is perhaps less obvious, is because now your solution has got 2 machines, it's naturally concurrent and it's naturally distributed. And suppose you want to build fault-tolerant software, you need to learn about concurrency, you need to learn about parallelism, you need to learn about distributed programming. And that's not because you wanted to, it's you must.
Yeah.
Right.
So a lot of the features of the language came about because that's the way we decided to solve the problem. So the problem was there, so how do we solve it? So you need concurrency, because the problem is very concurrent. You need the fault tolerant. You need the error handling so you can build the fault tolerant system. You need the distribution to build even more fault tolerant systems. You need things like hot co-loading, because you can't take the system down and do those changes. And it wasn't what we'd planned. It was the requirements. And also we discovered we couldn't find any other language or system that had these features. That's why we ended up doing our own, because there was nothing else.
So in the process of all of this discovery, what was your favorite part? Was your favorite part uncovering these new...
What
was your favorite part? What was your favorite part of the entire process?
I think it was when... I also was great fun getting users, Sheshkin and the first gang, because that was what made the difference, you see, because up to that point, it was just an experiment. And I don't want to write software that nobody uses.
Right.
It's a waste of time. And users provide feedback, and they allow you to test your ideas, because that's, the bullet stops if with the application. And so we got the users, and that was, we were kind of generating ideas and trying them out and pushing them out to the users. And it was rather like the early days of Unix, when what was kept in Unix was what was used, because you didn't have big resources. More or less like Erlang. We put stuff into the language, tried it out. If they didn't use it, we pulled it out again.
Right.
So what you see today, the link mechanism and things like that, we must have tried 20 or 30 different mechanisms.
Lots of stuff for doing
Lots
that.
of things.
Other communication mechanisms. Do you remember pipes?
Yes, I remember pipes.
The big it was
muff pipe, I remember,
yeah,
joint
pipe,
pipe, and the pipe algebra. And
it was our solution.
Don't see any of that today.
It was our solution to a problem we thought they had.
But they didn't have that problem.
So we invented all this great concept of pipes. We gave it to them and said, came back and said, did you like it? And they said we couldn't use it.
So we took it out.
And the reason, of course, was we had just misinterpreted what the problem was.
I see.
And that happened a number of times.
And then we did pragmatic things. We'd do an optimization, you write a heck of a lot of code and find it's only 2% better, but it's more complicated, so we'll chuck it out.
And the end is everything that's in our language, in the system, and the system design is there because someone actually wanted it. It's actually being used. And we got rid of stuff. Apart from priorities. Well, it's there.
And macros.
Well, macros people use.
Yeah, well, they should.
I know. I know they should. I know.
Where's the camera? Do not use macros.
and actually, on the way, we got rid of a lot of stuff that just failed or wasn't needed. So we just got rid of it.
Right.
And one of the things we found was that our attempts at making solutions were usually wrong. So it's better to provide the tools and let the people writing the application build their own mechanisms on top.
Right.
I mean, that's the joy of the conference. You go there. We've built the basic infrastructures, and then sort of let's see what guys can do with it. And they come back with fantastic applications.
Yeah,
so it's really amazing stuff.
Most of the applications people do today are things we never dreamed of doing. So that's really fun.
That is.
I saw a couple of really great presentations yesterday. That
completely
blew my mind.
Yeah.
I mean, those visualizations of parallel processes.
That was wonderful. That was fantastic. Yeah. And just the other things, all the products people build with it.
Yeah.
Just surprised every time. Say, wow, how'd they come up with that idea at all? That's great.
And then it's kind of they're surprised that it was so easy. And they come to us and go, oh, we built this system and it's easy. And we go, well, we knew it was going to be easy.
That's what we made it for.
That's what we made it for.
Yeah.
And then the reason it's easy for them is because they're tackling problems that were like the problems it was designed to tackle. So it's not surprising that it's easy.
This is a nice segue into the next section, which is the relevance of Erlang in today's world. And we touched on this a little bit in the introduction, but tell us what you feel the key strengths of the language are.
Concurrency and fault tolerance.
Literally.
I mean, I know we used to talk a lot about the functional side of it, and that's good, and it enables other things. But I'd say the concurrency and the fault tolerant mechanisms.
Right, with languages like Clojure and whatnot.
I mean, we saw that in some of the talks that the guys building big data centers, they're just buying new hardware, and there's the guys saying, well, we've got the latest hardware, 24 CPUs on the cards. And then they got the idea of measuring the utilization, and they find, hey, only one CPU is doing anything. And that's because they haven't solved the concurrency problem. So the whole industry is doing the wrong thing about